Hi everyone, I hope you had a good lunch. I'll just wait a couple of minutes if people are still so what I'm going to do is I'm summarize the initial MPI-IO exercises, and I have a talk which isn't actually on give me 1 second, apologies for this. I have some summary results, but I realized that I recently developed a talk which was much more useful. I gave it as a so I actually gave this. I summarized the results from a study we did in a virtual tutorial, a webinar I gave a month or so ago. So I thought that would be useful just to show that as the best way of summarizing the results. And as ever, I am there we go. Trouble. So I'll provide a link in the material to this. This is online with a recording, the whole talk, but I'll just go through some. So I actually benchmarked here. So I did two things in this talk. I compared to the previous system, the Archer, the Cray, which was the predecessor, and I did ARCHER2. But I also had access to this NVMe, the solid state disk storage, which has got 20 OSTs, and they're smaller, but has 20 OSTs. But I did a couple. This is the slides you've already seen. But basically, I tried to. So Giove, sorry, apologies if I'm pronouncing your name wrong. Giove mentioned just in the chat that he thought the results for MPI-IO were disappointing, and they are disappointing. And we're in touch with Cray about this, with HP about this. And I think the reason is on Archer, okay, a single process could write about 500 megabytes per second, which is a lot lower than we have at the moment. But a single OST could stay only about 700, okay? So in fact, a single process could basically saturate an OST. So the OSTs were very slow. However, there were lots of them. There was about 50 of them. And so you could get very, very high I/O rates because a single process could saturate an OST, and we could run on lots of nodes, lots of processes. The problem is on ARCHER2, the OST bandwidth, we have a much, much faster but fewer OSTs. But the single process bandwidth is nowhere near that. And so we'll see that there seems to be a setting which I have struggled to fix in the MPI-IO library that assigns one process per node to write. And that is that's suboptimal on ARCHER2, where it was absolutely fine on Archer. So if I jump forward to the actual results, that's file per process, which I've so I think I asked you to look at I think so if you just run out of the box, okay, the default performance is terrible on more than one node, okay. The bandwidth is drops by two orders of magnitude. It's totally unusable, and that's because the MPI collectives were not tuned. When we do MPI-IO, you can imagine there's going to be a lot of data shuffling going on. You have to shuffle the data around an awful lot, and it does that with MPI collectives. and they were not sure. So there's a magic setting which is in the default script. Export fi. This is 60. Okay, that's something. So that's already there. So you don't see the terrible performance. You see something like this. Now, what we should look at here is this. Let's look at the thing on the right. This is the disk, the gigabytes per second against the number of nodes for. Sorry, the one on the left. Apologies. So we'll see that you can actually the default. The other thing which I'll come back to is you can actually change the MPI library, the lowest layer on ARCHER2, from something called USF. The default is OF5. So the results you'll get by default are the yellow and white. So what we see is that unstriped, okay, doesn't matter how many nodes you run on, okay, you don't get any performance benefit. That's not surprising because, as we saw, we're just saturating. We're not benefiting because we're just we're writing to the same disk, and so we're not benefiting from that. We would expect that the bandwidth increases with the number of stripes, and you'll see for 12 stripes OFI, it sort of does. We get 4, but it's not very good. So the results are a bit disappointing. The bandwidth does go up with the number of stripes to about 4, and I think that was the figure that Jovi mentioned, but it's really not that brilliant. So I think you would have got results like the blue circles and the two yellow curves here. Limited use about 4 gigabytes per second, which is a lot down on the peak, way down on the peak bandwidth we'd expect from the file system, which ought to be able to support hundreds. So, okay, so those are the results you see which are disappointing. And so I'm now going to try and cover why they're disappointing, and then try and see if we can fix it to some extent. So again, as ever, I have too many windows open. Okay, so I think we should be that's it. Fine. Okay, so where are the bottlenecks? But we saw that a single process can only write at about just over a gigabyte per second, but the bandwidth of the node and the OST was up in the sort of 10 gigabytes per second. So there's an order of magnitude gap between what a single process can write and what you can get out of a node or onto an OST. So as a caution, benchmarking is very difficult, can be non-reproducible. You're sharing the ARCHER2 system with other users. Someone else may be also writing the same OST. Someone else may be using the same network links. So actually, those results I showed you in the talk came from 10 runs taking the maximum. I mean, actually, I did it fairly quiet time, so it wasn't too variable. But you can caching can give very high I/O rates, especially with small files. So if you want to get results, ensure that will run for a reasonable time, a few seconds, and repeat them several times. However, you do need to be a good citizen, and I actually got told off at one point because I was doing so much I/O, it was hammering. Just as a benchmark test, it was making the system unusable for other users. But I mean, that just the sort of hints. It is one of the more difficult things to do, is to get reproducible runtimes from I/O. But I basically take the max to basically run into this, or at least you get an idea for what the what's possible. So the ARCHER2 hardware. So we saw that it has we've covered this before, 3 separate work systems, each has 12 OSTs and 1 MDS, and you'll be assigned to a different one. There is this additional SSD file system which I was able to benchmark in that talk, but I don't believe it's available for user service yet. In fact, I can actually just test that if I get onto the I don't think it is. It's a bit confusing, but I don't think it's configured yet for general storage. Did anyone use? So serial I/O, you're not using if you're not using any parallel libraries, e.g., a single file with a controller I/O or file per process, there's little point in striping the file. For two reasons: A, with a single file, the performance bottlenecks appear to be elsewhere. If you're writing a single file, then basically you're down to this 1.2 gigabytes per second. So that's way less. There's no point using multiple OSTs because that's less than a single OST you can do. Multiple files, there's no point in striping. Remember, because it's already parallel as we're using many disks. So having that double parallelism, it doesn't help. Okay, and this is why single stripe is the default. And we've said a ballpark figure, a single process can achieve about 1 gigabyte per second in the absence of caching, i.e. writing very large files. The MDS can become overloaded. On Archer, the MDS was very underpowered, that was an issue. But on ARCHER2, it's a lot better. But opening and closing a file requires access to the MDS, which is a serial operation. Okay, basically, if you ask to open 1,000 files, then it will have to do them one by one, and that will become a serial bottleneck. Oh, sorry. So let me stop and read. I can see them here, but okay, fine. Okay, there may be the network. Fine. Okay. So yeah. So the one, and you share the MD for all users on the same file system. So if you're a user you may never have heard of might be on the same file system as you. So it turns out that on Archer, the MDS performance was so poor that file per process stopped scaling it relatively early on. ARCHER2, in my opinion, somewhat unfortunately, it can cope with that. But the thing which absolutely kills the performance is multiple open seek close operations. We have seen applications, OpenFOAM being one of them, where one of the access modes is each process will log to a file and will do that by opening, seeking, writing, and closing. And that is an absolute utter disaster. I mean, if you ever do ls minus l on the system and it takes a minute to, somebody's doing that kind of suboptimal use. So tricks: try not to write too many files. A very good trick actually is a simple trick is file per node rather than file per process. I mean, there are 100. That will reduce your number of files by more than 2 orders of magnitude. So if you don't really want to do genuine parallel I/O, I would say that doing a file per node is pretty good, or a file, a number of files per node. But I mean, that means that there's probably not too much data per node. You might just be able to do a gather and write them. But I mean, so if you've engineered your code and you don't have the ability to change it to use a parallel I/O library, file per node is much better than file per process. If you have lots of files, consider multiple directories, e.g. a directory per node, because looking up a file in a directory is a serial operation. It has to trawl through all there's a list. So it's a serial operation. So again, if you do have lots of files, consider multiple directories, and again, a directory per node. That will help quite a lot. So that's relatively useful. Stripe size, the default is 1 megabyte. That might seem quite small for very large data sets. You can experiment with larger settings. I don't set it too large, otherwise you won't be using all of the OSTs. If you have a huge stripe size, if you have a gigabyte stripe size and you have a 3 gigabyte file, it can't use more than 3 OSTs. I have not seen significant benefits from changing the stripe size, I have to say. I was surprised because to me, 1 megabyte for a multi-gigabyte, I mean, if I'm writing a 64 gigabyte file, that's 64,000 stripes. In other words, 3,000 or 4,000 per OST. That sounds like a very large number, and I thought that that would affect performance, but I haven't. That hasn't appeared to be an issue. So again, you may be worth for your application doing that, but I haven't seen any particular benefits from the test that I've done. So how does parallel I/O work, at least for MPI-IO? Well, the first thing is MPI-IO auto-configures to the Lustre settings. That's why I don't recommend using the hint thing. Basically, MPI-IO will basically, I'll just check out, but yeah, it will basically say if it sees that you're writing across 12 stripes, it will nominate a particular node to write to that stripe. And these are called aggregator processes. You don't see this, it's under the hood, but basically it spreads them across nodes if possible. So basically MPI-IO says, look, it thinks the optimal thing to do is to allocate one process to write to each stripe, and it will then gather the data, all the data for each OST. Well, which the stripe, sorry, it will gather all the data to be written to a particular OST to a particular aggregator process, and it will write to them. So it means that processes are not writing to the same OST. So that minimizes contention. If you have one I/O process effectively per OST, that will mean there's no need for any locking and such like, because you know that only one process is writing. Unfortunately, but we've seen that the single process I/O speeds on ARCHER2 are rather low. So unfortunately, that's an issue. But anyway, that's for later. The second thing is that it actually uses MPI collective to aggregate the data. You can imagine that you've got a hopefully you can still see my camera. Yeah, that you've got a process who needs to write data to an OST. It needs to gather that data from lots of other processes. So maybe it could just do an MPI gather or something like that. Then performs a small number of large write operations. So all this is only possible with collective I/O calls. If you don't do collective I/O, it can't do this data aggregation. It can't do any of this clever stuff. If you're worried about what's going on, you can get useful runtime stats by setting this variable MPI-CH MPI-IO stats equals 1. And at runtime, that will print out what MPI is doing. MPI-IO is doing, for example, it will print out how many aggregator processes it has, where they are. It will print out statistics about your I/O, how many transactions there were, how big they were. So that's a very useful trick to set that variable, and you get useful runtime statistics as to what MPI-IO actually did, and that does sort of help you understand what's going on. So, for example, okay, if we had this 4x4 array on a 2x2 process grid, okay, what MPI-IO would do, and we striped it across 4 disks, 4 OSTs. MPI-IO would first notice that we used, and when I say MPI-IO, this is inherited by the other I/O libraries. They use MPI-IO at the lowest level, so the same is true for, in most cases, for the other I/O libraries like HDF5, for example. What we see is, first of all, it says there's 4 stripes, 4 OSTs, so I'll nominate a process for this stripe, a process for this stripe, a process for this stripe, a process for this stripe. Then the data for this stripe, this disk, will be gathered, that data there, and then written as a single write. The data for the second disk will be gathered, this data here, done in a single write. The third disk will be gathered, and then the fourth data for the fourth, well, in parallel. And that is good because it means all this I/O can take place at the same time, because we know that there's no contention between the different OSTs, between the different disks. So this process can write merrily to this file, to this part of the file, this part, this part, and this part. And so in principle, that should work really well. But unfortunately, as I've said before, by default, Cray MPI, I say Cray MPI, it might be lower level than that, but it uses one aggregator per stripe. So that is an issue. We've seen that the IO, single process IO is very slow, as we've seen on order of magnitude down on what you'd hope to be able to achieve. So this default can be changed using a slightly arcane syntax. Unfortunately, it didn't seem to make as much. So what you can say is you can do export MPI-CH MPI-IO hint equals star means for all files, Cray CB nodes multiplier. I don't know what C means. It's sort of, but the aggregators equals 2. What that would do was would use twice as many aggregators. And if you do MPI-IO-CH stats equals 1, you can see where they went. And it does something perfectly sensible. It puts, for example, 2 aggregators per node. But I haven't tried this for a few months, but I saw very little benefit from that. And I think the reason is that one aggregator per stripe. One aggregator per stripe is nice because it means that you only have one process writing to each disk and there's no locking. If you had 2 aggregators per stripe, you'd have 2 processes writing to the disk, and then you'd need to maybe worry about contention between them. I think that's the reason. It's still not entirely clear to me. The other thing you can do, so for example, I put this, the default low-level network layer is called OFI, stands for Open Fabrics. And we have seen this isn't about I/O, just for general MPI calls, it can sometimes have poor MPI collective performance, particularly in the case where you're using large data buffers, large amounts of data. So the fix is to set this bizarre internal variable to be 64K. I can't remember what the default is actually. It's much smaller, and this helps the performance of collective I/O on ARCHER2. Of collective MPI collective routines, and hence improves the performance of collective I/O. However, you saw that fix was already in the default script if you'd looked, and it still wasn't brilliant. We can actually, this is unusual now on the Cray, maybe very specific to ARCHER2, this particular generation. But there are two, at the very, very lowest level, there's some protocol used to send data from node A to node B. The default is OFI, Open Fabrics Interface, but there is an alternative transport there called UCX. I don't quite know what it stands for, but it's developed by Mellanox. And it seems to be better in the case where you have collectives with large amounts of data. So it is actually possible to use this different transport layer. You have to swap some modules, but you don't have to recompile. So, you do module swap Cray PE network OFI, Cray PE network UCX, and you do module swap Cray MPI-CH, Cray MPI-CH UCX. And that switches out the OFI layer and switches to the UCX layer. And we have seen that for collective communications, that can have a benefit, and hence for MPI collective I/O, that has a big benefit. So that is something that's worth looking at. You might ask, why is it not the default if it's better? Well, it's not. So this is a global change for your whole code. So we've seen that for point-to-point communications of small amounts of data, it's maybe not as good as OFI. So it's a bit of a, the nice thing is you don't need to recompile. So you can actually just do a benchmark test run and do it again with these modules and see what's quicker. But it is very dependent on what the balance of your code is, and how much time does your code spend in different sections of perhaps halo swapping versus I/O. Common mistakes. So these are the classic things we've seen from queries to the help desk. First of all, text data files. Text data files are just really slow. So that's a no-no. Write binary data. Multiple accesses to a large number of small files. That was what I sort of said before. Sometimes people have a model where every time they update a file, it's open, seek, write, close. That is really not a good thing to do. If you've got lots of small files, you should open them at the start, keep them open all the time, just keep writing and close them at the end. The other error is using stripe for serial I/O. People may have heard about striping and thought it would increase their bandwidth, but as we've seen, if you have serial I/O, the bottleneck is elsewhere. The bottleneck is in the per process bandwidth. So there really isn't any point. So then people switch to parallel I/O, maybe use MPI-IO or HDF5, and then the classic issues we see there are using a parallel I/O library but not striping the file. So people say, we saw that for MPI-IO, if you didn't stripe the file, then you got no scalability as you increase the number of nodes. And actually, I would recommend full striping across all OSTs. On Archer, where we have 50 OSTs, you could argue that full striping was overkill and introduced its own overheads. But with only 12 OSTs, to be honest, I mean, I benchmark an intermediate number just for completeness, but in practice, I would recommend, either using serial unstriped I/O or fully striped. The other one is using non-collective, i.e., individual I/O to a single file. That again, we saw that the performance of non-collective I/O is terrible, and that will translate into HDF5 and other libraries. You should enable, and we'll have a small overview of how to do that in the next lecture. And you must quantify performance in terms of gigabytes per second. So we sometimes get people sending queries saying my performance is very slow, it takes 5 minutes. I mean, that's not really helpful. We need to know, it gets, and we had cases where people have said my I/O is very slow, and when you get into quantify, it is in the tens of gigabytes per second, and you're saying, well, actually, that's quite good. So you should be able to achieve something around 10 gigabytes per second for parallel I/O. Now, I know that the maximum bandwidth of the entire disk file system is over 100, so that's not pushing the limits, and we are trying to work with HPE to understand how we can alleviate that. But you should be able to achieve around 10 gigabytes per second for parallel I/O to a single shared file. That should be the kind of number you're getting, and if you're not, then something we could look at. So as I said here, this is really the conclusions. For parallel I/O single shared file, use a high-level parallel library, use collective calls, and stripe across all OSTs with that -1. And why it's nice to use -1 and not 12 is you go to any system, you just specify -1, you get all the OSTs, as opposed to having to remember, how many there are. For serial I/O, single or multiple files, do not stripe the files, which is the default on ARCHER2, but you should check on your system. It's possible the default is multiple stripes. Consider writing file per process, file per node. Controller I/O only uses a single disk, but file per process may overload the MDS, especially with many users. So consider file per node or multiple files per node. But I mean, I think you should try and get away from writing as many files as there are processes. You may be interested to know if I can maybe share. There's a slight quirk on ARCHER2, which I will now explain. So that's it's taking a while. That's my window on ARCHER2, okay? So if I do ls -l, there's bench IO, for example. bench.io and the executable, let's say bench.io.f90. Is that what, does that output look like what you would expect on a sort of standard Linux laptop? I don't know if people have used standard Linux, but there's something which looks different from the in terms of any way it looks different. I mean, it might not jump out at you, but I don't know when anyone can see what might be different. And at least on Ubuntu, the default is to color the files. So I can't remember how it works, but executables are one color, plain files are another color, and different files are a different color. So okay, so that's an input. What I will do, so I'll do two things here. That's a very so let's just show you the, so for example, so I'll come back to that question. The standard thing that you get for is something like this, where it's colored them. Okay, now to do a cut, to color it, it has to inquire the status of the file. Yes, alias, alias, color. Yeah, exactly. But inquiring the permissions on a file, like is it executable, or is it a directory, or is it whatever, requires contacting the MDS. So if we had alias ls equals ls minus minus color equals auto, every time anyone did an ls, it would be querying the metadata server. And we found on Archer that literally that killed the metadata server, just having colored output. So we disabled that, and there's some way of but that you should not do that, because it will harm other people. It's if you ls a directory of 10,000 files, it needs to look up the metadata server 10,000 times. So the SR is to do with permissions. So it's so there's I find Unix. I'll go back to that. So Unix has an absolutely ancient, security model where it tries to cram all this information into a few bits, but doesn't it? It's to do with permissions. The S is a sticky bit, and it basically means it inherits permissions from above. So it will. It means that it basically stops you breaking the security model. So it will. So that means that's the group. The group access is fixed in some way. So it inherits. The sticky bit means that bit is always set, and it means it's inherited down the tree, and that's done to make sure you don't that when you create files, they're done with the correct permissions. But I can never quite remember exactly how they work. But it's to do with that, yeah. So if I actually go to, this is my home directory. So you can see that, yeah, that my home directory has this big sticky bit. So I think that stops you changing the permissions to give bigger access. It's something to do with permissions being fixed or inherited down the tree, and I can never quite remember exactly how they work. So it's not a very satisfactory answer. I would also, as someone who's been using Unix for almost 40 years, the fact that Ubuntu does an alias of ls to ls minus color is appalling. should never alias an inbuilt command ever, 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 ever. But anyway, that's what they did. There you go. It's terrible. It means a lot of shell scripts won't work. You should not alias system command. You should never do it. It's just a road to disaster. But they've done it just to make them, just to give nice color output. Isn't that nice? So anyway, so that was the end of that talk, and hopefully the next the exercises to try and put some of these things into practice. I will say ahead that none of them are going to entirely fix the problem. They will alleviate the problem, that we can get up to maybe 10 gigabytes per second, especially if you go to maybe 16 or even 32 nodes. Well, at least definitely 16 nodes. You should be able to get up into 10 or more gigabytes per second. But as I said, this design feature that MPI-IO picks one aggregator per stripe, and hence a maximum of one aggregator per node, at least for large numbers of nodes, is not optimal. But at least it will improve the rate by a factor of 2 or 3. So I will just briefly share the exercise sheet to see what we want to do. It does take me a long time each time to find this. I don't really understand why I'm so slow. There it is. So now I configure Lustre file system. This is, you can export MPI-IO stats equals 1, which will give you information on what's going on. Does increasing the stripe size have any effect? I don't think so. Try using this. You should see a benefit. Again, I would recommend running on relatively large numbers of nodes, at least 8 or you need to run on to exploit the whole file system. You need to run on as many nodes as there are OSTs at least. And so we have 12 OSTs. So it's not till you get to 8 or 16 nodes you're going to be, I would say 16 would be a good thing at the moment. And here's this trick where you can try and say, look, do more do more aggregators per stripe, more aggregators per node with this hint. Although, as I said, I've got none of these to me was magic, but this one especially didn't seem to help at all. But this to me, and running on large numbers of nodes, where I got figures of 10 or more gigabytes per second. So just to check, I had is user Piccanil online? It's no big problem. It's just that I think that we had this problem. The quota was exhausted, so jobs were failing. So we had a catch-22 that because jobs were failing, it meant that the files weren't being deleted. So I don't know who Piccanil is, but I think you have quite a few files lying. It's not your fault. It's because my script should have done the tidy up and it didn't. But actually, I don't. Maybe I can find out who that is. So I have fixed that. We do have a much larger allocation now. It was partly my fault. We had I did ask for a large project allocation, and I was given it, but I hadn't enabled. You have to actually enable it, which is I'd forgotten that you had to enable it by hand. Oh, I can't actually see. Oh yes, JG Piccanili. So they don't seem to be online at the moment, unless that's Joseph L. It's not disastrous. Oops. That's not what I meant to do. That's okay. If that user, if you're around, if you could maybe just go and delete some of the directories. As I said, it's not your fault. It's an issue with the fact that I will update the script but we do have some overhead now. But I think they were caught by this thing. So the schedule now is just sort of 20 minutes to play around with that benchmark. I will summarize the results and then give the final talk, and then we'll finish at 3:30. So I'll put a quick note up. And as I said, after the final lecture, there is plenty of time to, if you want more general questions about what your IO problems are. I mean, you may have noticed that these are all very structured problems, very deliberately simple 2D grid on a 2D array on a 2D grid, a 3D array on a 3D grid. You know, if you're doing an engineering calculation, you have a much more complicated, possibly finite element unstructured mesh. All those things can be done. They're just in the spirit of it is the same. It's just a generalization, but the general approach is the same. Just the details are different. Okay. So I'll hide my camera. I am online. I am online if you have a chat message. Hi. So yes. So yeah, that's yeah. So as I asked if anyone had, I was about to ask if anyone had any results to share, but you're right. Strains of perform worse with more than one aggregator. So yeah. So as I said, I think the problem is that one aggregator per stripe is a sweet spot. Sorry, it's not a sweet spot. Although it doesn't have the best bandwidth, it does mean that you don't have to. It does mean that MPI-IO knows that only a single process is writing to a single disk, and so there's no locking involved. There is a way to tell MPI-IO, trust me, I'm doing collective I/O. You don't need to lock at all, and that is supposed to alleviate this, but I couldn't get it to work. Again, it's something we're following up. Yes, all the benefits seem to come from switching to UCX. So what's your only other problem is previously I saw instability for UCX at 30 or greater, but what's the best bandwidth? Anyone? Whoops. I will switch back to that lecture and start showing. I seem to have closed that. Okay, that's silly of me. Okay. Okay. So yeah, 9 on 16. Yeah. So I'll share my screen here. Yeah. So give me a second. So this is comparing disk and NVMe. We don't have access to it, but if you look here, you'll see that the UCX is the 12, that, and well, again, for unstriped, it makes no difference, but you see significantly better performance when we go to, so I got over 10, but that would just be, you know, that's effectively, with variation, that's about 9. An interesting point is, you'll note that with 4 stripes, yeah, we don't get better bandwidth as we go beyond 4 nodes. That's because it's only assigning 1 aggregator per node. So although this is 8 nodes, there'll be 4 aggregators, 1 for each stripe. So you would expect, that's an interesting thing to see. I would expect that this would tail off as well beyond 16, but I wasn't able to get that data point. But the fact that this data point rises not linear, but rises with node count until 4 and stops, is because we had 4 stripes, and you would see the same effect at 2, I think. But yes, you're able to get of order 10 gigabytes per second with using UCX with full striping on, I would say, more than 12 nodes. That is sort of what, now that, so the numbers all make sense, you know, that we get about 1 gigabyte per second per node, because we only have 1 writer, unfortunately, and we have 12 nodes, so that's 12 gigabytes per second. With a bit of overhead, it's of order 10. But that is, you know, sort of, you know, a ballpark figure is parallel bandwidth is serial bandwidth, which is 1 gigabyte per second, has the minimum number, the number of stripes, number of nodes. That's sort of, you know, what you see here. Unfortunately, this is not. This is still about only 10% of the available bandwidth, and so, you know, here I went about, you know, varying the stripe size and number of aggregators, but I had no. So, for example, I think, as Jove said, I also tried a different number of stripes, which didn't help. But this is my data point. If I go to this lock mode, one is also changing. I haven't talked about here. It's also changing the lock mode to try and say, look, you know, it's safe. You don't have to lock. But basically, you basically, as you increase the number of aggregators per stripe, I went up quite high, you see a decrease, and I think that's because of contention, unfortunately. So, you know, 10 is about the maximum you're going to get. And as I said, all these things are slightly disappointing at the moment, but we will be following them up with HPE, because I don't think it's a fundamental. It ought to be better than that. It ought to be. And why we didn't see this on Archer was that on Archer, a single process could saturate a single OST, whereas on ARCHER2, a single process has an order of magnitude less bandwidth than a single OST. And that's the reason why the ARCHER2 configuration is not good for Archer configuration, not good for ARCHER2. I only discovered this in sort of late May, and we haven't just, when there's an outstanding query, we haven't had a chance to follow up in any detail, but it is important to follow up. So apologies, they're slightly disappointing, but I think that it's useful to do these things because you know, your mileage may vary on different systems. So I think, you know, these are all things that you might want to try on other systems. You know, so although these tests here, varying the stripe size, varying the number of aggregators, various locking mode, I will put a link up to this talk on the GitHub page, didn't benefit ARCHER2. If you were on a system where maybe wasn't a Cray system, or where you had better bandwidth from a process, or many more stripes, that all these things might help. So it's slightly disappointing on ARCHER2, but in general, there are things which would be worth tuning. That's why I left them in the exercises, even though they don't really help here, unfortunately, other than the switch of the MPI implementation. In general, there are things which you might want to try. So does anyone have any final questions before I just give the final sort of summary talk? So it did work on version 2. That's great. Okay, that's good. There's been a software update then. So yes, so you've got 9 gigabytes again, because there are only 12 OSTs. So once you get more nodes than OSTs, oh, well, actually, that's interesting. Yeah, so the fact that you get no benefit from having more nodes than OSTs, basically. And so that's why, that's a nice data point. Thanks, I wasn't able to get that. So yes, so that I would have predicted that 9, I would have predicted that 8, that 1632 got the same bandwidth, because for the same reason that 4 and 8 got the same bandwidth with 4 stripes. You've reached that's this formula here. Parallel bandwidth is the 0 bandwidth, so it's the minimum number of the stripes nodes. So if nodes is bigger than stripes, it doesn't increase. Okay, thanks, that's useful. I should rerun my tests, that's useful. So the numbers are the same, but the stability is better. Good to know, thanks. So I will give the final talk. Again, apologies for me taking so long to switch, but I am still really getting used to my my new laptop. Right. So, I have talked about MPI-IO, partly because that's the thing I know most about, most experienced with, but also it is the underlying layer for HDF5 NetCDF, and in some modes this ADIOS2 library. I'll point out the caveat in this talk. So I would expect that, with one exception, which I'll cover here, sorry, no, you can't do ADIOS2. So I would expect that for my bench-IO benchmark, the results will be largely similar in NetCDF and HDF5. There might be some small overhead because you've got extra software layers in there, but to a first approximation, I would expect the graphs to be very similar, i.e. best with UCX, best on more than 12 nodes with full striping, but about 10 gigabytes per second. So this is really quite a short talk. So I'll talk about the issues with MPI-IO, I'll talk about HDF5 NetCDF. So apologies, the title slide is wrong. Apologies, the title slide is from the previous time I gave this course. I have not updated this slide correctly. Just give me a second just to check I haven't made a complete howler. No, I have. Okay, so this is the right talk. Apologies, it's just I've left in an old comment. I apologies with that. So I just check I'm doing the right thing here. Sorry, I'm scribbling forward just to check that I updated this slide with this. Yes, this is the new lecture. I updated it yesterday. Okay. So I updated this lecture yesterday briefly, but I missed that, however. So I'm actually going to talk a bit about the issue with MPI-IO. So, as I said, interestingly, if you did an ls-l on an MPI-IO file, you would have seen it was exactly the same length you would expect. If for a 256 cube data set, it would be 256 cube times 8 bytes long. So the files are just raw bytes. Of course, you could put header information in yourself, but by default, they're not. And again, the storage is architecture specific. So if you have a big or little ending floating point, then you will not be able to easily transfer it. This means it's difficult to deal with in other codes downstream. What I mean with this is that, if you want to visualize these files, you have to do it yourself, okay? Because you have to write your own post-processing tools. The advantage is it can be very fast, but it's good for checkpointing, but if you wanted to take this code offline, put it through a visualizer, for example, as a post-processor, it would, your visualizer would just say it's a file of 64 gigabytes. Well, I don't know what it is. What the heck is it? So that's why we have higher level libraries to find high level formats, which have things like standard metadata. So there'll be headers on it saying things like, this is a 4x5x7 array of doubles, and that is very useful because it means that you can use standard visualizers. So, for example, things like ParaView and such like will get a lot of it. They will be able to look at a file in HDF5, for example, understand what it is, and display it correctly. Or, for example, if you're doing climate or weather research, they tend to use NetCDF. There's a whole bunch of tools for visualizing and processing NetCDF files. So, it just works out the box. However, the people who write HDF5 and NetCDF are not going to go away and reinvent parallel I/O. It's far too hard. So what they do is, at the end of the day, they layer on top of MPI-IO for performance. So they put a higher level layer on to make it more easy to use, maybe an easier interface, and add metadata to the file. But to get performance, at the end of the day, they call parallel I/O. They call MPI-IO. So many real applications use higher level formats. HDF5 seems to be very popular these days. But I still think understanding MPI-IO is useful because it enables you to get performance as well. The things we find out about HDF5 is the common denominator of all these things. So if it works for MPI-IO is the common denominator of all these things. So if MPI-IO works well, if you can understand MPI-IO, how it works, you should be able to get the right, for example, striping and such like for these other libraries. So HDF5, I got from Wikipedia, is a set of file formats, well, HDF, designed to store and organize large amounts of data. I've not used them a huge amount myself. Well, I've worked with them with user codes, but I've not actually written anything myself. But the data is arranged like Unix file system. It's self-describing and hierarchical, and it can use MPI-IO to do the I/O. So basically, it can be like a whole file system, and each, you could say, as it says here, you could, data can know, it knows whether it's a table, 2D array, a raster image, a three-dimensional array. All these things are taken care of, and that's done so that you can then write standard post-processing and analysis tools. So again, you'll see in if you look at the benchmark. Now, I apologize, this is in Fortran, but it will be very similar for C with a few underscores missing. Parallel HDF5 is very much like MPI-IO. You describe the global data set, you tell it this is how big the whole data set is, and then each process describes its local portions of the global set. Now, there's a bit more setup and such like, slightly more flexible, and there are a few more I/O calls, but HDF5 calls them hyperslabs. MPI would call them subarrays, which you would define using an MPI subarray type. HDF5 calls them hyperslabs. So what you do is, if you want, how you describe these, so the file space is global data that includes there are setup calls. This file space is an object which defines the global sizes. This is basically the same as MPI or the Fortran. It tells HDF5 you've got a Fortran code. The offset is, if you've got is the starting point, and this is, I'm just doing this with a very simple cube example. But if you're selecting a subcube from a big cube, you need to know how big the big cube is, how big the subcube is, and where it starts. So offset is the start, and count other subsizes. Okay, so that's very the same. When I originally wrote my benchmark for MPI-IO, but when I converted it to use HDF5, I had all the data lying around. Okay, then you have to call a collective write, and again, these hyperslabs can be merged to create a global file. And the same thing, the collective, you have to make sure there's multiple write calls, but you should use the collective write call. And HDF5, the actual file I/O is done through MPI-IO, and you'll see that from the hopefully from the modules. If I share the exercise sheet, you'll have seen that the modules we had to load were create HDF5 parallel, so that is a module that uses HDF5 but uses MPI-IO, and actually the NetCDF library uses HDF5. So create NetCDF HDF5 parallel is NetCDF, which then calls HDF5, which then calls MPI-IO. So that's the hierarchy of these modules. So this module here is the one which makes sure that you interface to HDF5 to MPI-IO, or to the efficient implementation of MPI-IO on this system. Go back to my. So HDF5 is very general. As you see, it can describe an infinite range of formats, but some application areas have quite well-defined formats. If you're doing climate science, you tend to have large arrays. Okay, an array of data covering a lat-long grid over the globe, for example. This is maximum daily temperature. So NetCDF, again from Wikipedia, a set of software libraries and self-describing machine-independent data formats that support the creation and share of array-oriented scientific data. So this is built on top of HDF5, but it's more restricted because it's been designed specifically for a specific community. I say climate research, but also oceanography and GIS use it. And so there's a rich set of tools. So if you're doing that, if you're working in that area, this is the data format you'd use, because down the line there'll be a lot of data manipulation and visualization tools that you can use straight out of the box. And again, there are these sort of def var, power access, and put var. They look a bit weird, but I just copied this from somewhere else. But basically, this creates a file identifier, and you specify the global sizes at the start. So you're setting up. I mean, to be honest, these libraries don't often talk about files. They talk more generally about data sets. But I think but they're eventually stored on file. This says, I want to create a data set with doubles, and these dim IDs is the global sizes, how big the array is. You then have this setup call, which is the equivalent of specifying which subarray of the global array all the processes access. So collective means it's write all, and then this is setting up the access, and then when you actually want to do it, it's called put variable. And again, these starts is where the array starts, and these count for the subsizes. So you're saying, this is the global array. It's a big array. I want to do collective I/O, and when you do a particular I/O for a particular process, you say which subcube of the big cube and you can see it's quite straightforward. It's all designed for regular grid data. ARCHER2 is a much more recent parallel I/O library. I don't think we have an implementation on ARCHER2 yet. People have been using it on ARCHER2 quite extensively, but I think they may have to compile from source. We may have to look at that. So it can output using MPI or HDF5, and again, I haven't benchmarked this myself, but talking to colleagues, again, not surprisingly, you get the same. If you use, my understanding is if you use ARCHER2, if you output an MPI or HDF5, you get the same performance behavior as we have seen for MPI-IO. However, it supports its own formats, and the most recent one is called BP5 binary pack v5. And so it has the same overall approach. Each process defines what portion of the global data it owns, and you call read and write routines. But it's very configurable at runtime. So for example, if you want to switch from writing out an MPI-IO format to BP5 format, it's all done via a configuration file, config.xml. You don't have to recompile all the time. And I want to put it into Bench.io, but I haven't had a chance yet. But colleagues working in CFD, a colleague of mine, Paul Bartholomew, has seen potential benefits from BP5 format in other codes. In this code called XCompact3D, and the reason is that we saw that writing multiple files per node gave us good bandwidth. People were getting many tens of gigabytes per second, but we ended up with lots of little files, which was a bit of a nightmare. Shared file I/O produces a nice single shared file at the end, just like the serial file, but because of this low per process I/O, we suffered in terms of bandwidth. The BP5 format writes multiple files under the hood, so it writes lots of little files, so it can get the same, potentially get the same kind of performance as we get with file per process or file per process. But it writes metadata, so you can read it back in on a different number of processes. It will figure out what the issues are. Okay. So this may get around the limits of MPI-IO, which has a single shared file, but you don't suffer from. I was very anti lots of multiple files because they're a nightmare to manage, and you have to write your own pre and post processing. The ARCHER2 writes enough metadata, I understand, that it can do all that for you. So you don't actually see the fact it's lots of little files. You just see a directory with the right file name, but under that there are lots of little files, which presumably are the data on each node or something. I don't know. But that's why this does have a hope of getting many more than 10 gigabytes per second, because it doesn't restrict itself to a single file. It allows itself to write multiple files. Summary: MPI-IO may seem a little low level, but I've concentrated in this course because it's the building block of parallel on most systems and all the other libraries. High level formats typically build on top of it. I mean, people will put a lot of work into their MPI-IO library to integrate well and with Lustre, and to integrate well with their own hardware, and therefore, people who write on higher level libraries just want to inherit that. Common formats for HDF5, NetCDF maybe not so much, but depending on what community you're from. You might also want to look at the new ARCHER2 library. I am working towards putting that into the bench.io. But understanding MPI performance is key to getting good performance for HDF5 and NetCDF. So that's why I've concentrated on that here. That's the way to understand what's going on. And I will just, as we finish up, just a bit early, but I will basically well, there's the URL, yeah, but I will. This is the ARCHER2 page. So the interesting thing is it was funded in the US. So they were always targeting very large systems, exascale computing, and it actually is quite sophisticated because you don't actually have to write to file. You can use it to communicate between two applications. One application writes, one reads, and it never writes to file. It goes purely through, I don't know, over the network sockets. I'm not sure what it does, but it is quite sophisticated and having quite a lot of work done on it. So it's something that I would like to know more about, but I don't at the moment. And yeah, you can see it can write BP5, BP4, whatever, the HDF5, and it can also do MPI-IO as well, I believe. Well, you can read it yourself. It's a new format. It's a new format. But this config.xml file is how you configure things. So that's really all I had. Finished just about on time. That's been an hour and a half since our last break. So I'm happy to take questions now. But I'm going to take a break now till because I've been lecturing for a bit, until I'll be around, as I said on the sheet, till just about 4:30. I'll be around from 4 till 4:30. I'm happy to take questions now, but failing that. So thanks for attending. I hope you find it useful. There will be a survey form going around. As I said, we do appreciate feedback. We do look at it. If not, we do it. We'll have a regular weekly meeting where we review feedback. Good feedback is great. It makes us feel good, and we can tell EPSOC how great we are. But also, critical feedback is excellent because it allows us to we take it on board and, where necessary, improve the courses for future runs. So thanks everyone. I hope you found that useful. As I said, the accounts will be open for maybe another month or so you'll have plenty of access to play around. You may not have such a big disk allocation, though. We only give a big disk allocation for you. There'll be so many people running at once, and that may be reduced. So please delete files before you leave, if there are any lying around. And yeah, that's it. I'm leaving now just to take a break until 4, but I'll be around then, happy to take any questions.